Alright, we have learned on the line of symmetry and how to draw the line of symmetry. Next, we are going to learn on symmetry elements. What are symmetry elements? External shape of well-formed crystal may reflect the presence or the absence of certain symmetry elements. Basically, there are 4 symmetry elements. We have rotation axis, mirror planes, or also known as reflection. Then we have center of symmetry or inversion. And finally, we have roto-inversion axis. The presence of these symmetry elements can be detected in well-formed crystal by angular arrangement of the bounding faces and sometimes by the size and shape. But in poorly developed or distorted crystal, the symmetry is not that obvious, but can be derived by careful measurement of angular relations of the bounding faces. This figure shows the illustrations of the 4 symmetry elements. So in figure A, we have rotation, which is generated by rotating the original motif on the axis at 180 degree. Okay, so before you can draw the symmetry elements, you must have the axis. Okay, this is really important to have the axis. So we have X here, Y, and Z. Okay, then you have to know where is your original motif. Okay, you might be wondering why I'm holding this marker pen. So imagine this is my motif and the blue cap is the top or the head, and we have the white part can be the tail. Okay, so we have head and tail. This is my motif. So let's look at figure A. So this is the original motif and it is given that the rotation angle is 180 degree. Okay, for rotation, always look at the angle of rotation given. It can be 180 or 90 or 45 or even up to 360 degree. Okay, so 180 means it is like a hemisphere. Okay, so you have to rotate at 180 degree. Tada! So this is your rotated motif. Okay, get it? Then we have mirror. Okay, for mirror is very easy. Right and left hand motif related by a mirror reflection, or the easiest is you just stand in front of the mirror, so yourself is the original motif, then you have a mirror and you can see the reflected motif of yourself. Okay, then we have inversion. Okay, for inversion, this is your original motif. Remember, I said you have to know where is your axis. Okay, so this is X, Y, and Z. So this is the motif. And when you inverse your motif, okay, the inverted motif, you have to get through by inverse through a point, a center. So it must go through the center of your axis. This is the center. So it has to invert through the center. So you get your inverted motif here. Then finally, we have roto inversion. So that means you have to do rotation, then only you do inversion. In this case, the angle given is still 180. Alright, like I said, this is my motif, and imagine this is the head and the white part is the tail. So the same goes for the comma that we use here. So this part, the top part is the head and the bottom part is the tail. Okay, so this is your original motif. You have to rotate 180 degree, and then you have to inverse through the center of the axis. So now your head of the motif is pointing downwards and the tail is pointing upwards. That's why you get your final motif like this. Okay, simple. In symmetry elements, the internal order of crystal structure of a mineral can be thought as a motif repeated on a lattice. The motif or group of atoms has certain symmetry or lack of thereof that may be reflected in the crystal's external shape. For example, we have perfect cube here and distorted cube here. Okay, you can see the different external shape produced by systematic stacking of cubic unit cells. So you get a perfect cube and distorted cube because some part of the cubes are missing. So that's why it gives you distorted cubes compared to this one. This one is perfect cube. Three-dimensional internal order of a crystal can be considered as the periodic repetition of a motif or a unit of pattern in such a way the environment of around each repeated motif is identical. A simple and ordered arrangement of a motif in two dimensions is shown here. You can see here is two-dimensional order, and we use comma as the motif. Because comma does not contribute to symmetry elements to overall ordered pattern, only translation is present. In crystal, motif can be molecules such as water, anionic such as carbonate or silicate. It can be cations such as calcium ions or magnesium ions, or even it can be atoms such as copper, or it can be combination of anionic groups or ions, etc. These are the examples of symmetry in chemistry. You can see variable symmetry contents here as example. Many motifs contain symmetry. So we have rotation axis, mirror planes, and center of symmetry are examples of symmetry elements. Symmetry operations can then be defined as the act of rotation about an axis, the act of reflection by mirror, and the act of inversion about a central point. Remember, symmetry elements, we have four: rotation, reflection or mirror, then we have inversion, and finally we have roto-inversion, combination operation of rotation and inversion. Okay? And finally, the translation-free symmetry element as expressed by the morphology of crystal. So you can see this is six-fold axis of rotation, mirror plane, center of symmetry, and four-fold axis of roto-inversion. Alright, so we will stop here and have a break. We shall continue in a bit.